Welcome back. So we're gonna continue on with with session 3 on applications in lunar autonomy. We'll be going into our networking discussions. So we have 2 different breakouts available. There will be lunar perception and sensing, and then lunar environment. So if we're gonna just make 5 breakout rooms and randomly assign everyone a room. If you would like to be reassigned to the opposite breakout, just go back to the main room and do a verbal request or a request through chat, and we'll put you in the right place. In terms of our LSIC APLers who are facilitating, we'll try to get you guys into the right room as quickly as possible. But in that case, I think we're good to start the breakout rooms if we can. All right, welcome back, everyone. Happy coffee, if you got some. We're gonna move straight along into session 4 on challenges in autonomy. So this one will be led by our very own Johns Hopkins Applied Physics Lab, Stacy Tang. She's also part of the Extreme Access Focus Group over in LSIC. So take it away, Stacy.
Thank you, Danielle. So we have, again, 3 great panelists for session 4 for challenges in autonomy. So we have Julia Antoniou. Are you online?
Yes, I am.
Great. Becca Bone-McCarter, are you here?
Yep, I'm here.
Great. And Cam Dickinson. Cam, are you with us?
I'm here as well.
Great. We have all our panelists. So would you mind giving a little bit quick bio introduction of yourselves? Julia, I'll start with you since you're first.
Sure. So hi, everyone. Happy to be here. I'm an engineer at MathWorks, actually, which you might know better as the people who make MATLAB and Simulink and 100 other toolboxes that we have. And my particular job here, my degrees are in mechanical engineering, so I'm not the one, behind the scenes actually developing MATLAB, but I'm one of our externally facing engineers that helps others use MATLAB and see if it's a good fit for their work. And I work with engineers outside of MathWorks on their projects. So 100 Tools obviously covers a lot of space, so we all have our different focus areas. So for the last 5 years, I've primarily been working with engineers at government agencies and labs, NASA and APL being big ones for sure. And my focus areas are primarily, of course, robotics and autonomous systems and algorithm development, dynamic simulation, etc. So happy to be here.
Great. Great to have you. Becca?
Hi, I think I might have a slide in the master slide deck too.
Oh.
I'm Becca Bonham-Carter. I'm an embedded software engineer with a Canadian company called Mission Control. We primarily do software and mission operations for space and robotic applications. So I did put together a little slide. We'll see if it comes up.
Sorry, I think it should be the next slide on the list. Oh, maybe not. I can share it real quick.
Thank you, Danielle.
Yep.
So while we wait for that, Cam, would you have a quick intro for yourself? Oh, never mind. Sorry. Danielle's quick.
Danielle is quick. Thank you. So I wanted to add some visuals to my intro. So on the slide here, I've just highlighted some of the challenges and specifically AI on spacecraft hardware that we typically see in our work. And also one of our recent lunar and autonomy related projects, which is our MoonNet model, which was a technology demonstration of using neural networks for classifying lunar terrain that launched last December on the iSpace lunar lander. Some of you may know, unfortunately, that lander didn't, land successfully, but our team was really lucky to complete most of the work we were hoping to get out of that project, which was kind of testing out our workflow for doing this, the first deep learning model that was making it to the moon. So we got to gather a bunch of data from our moon yard. You can see some images of here, train it, deploy to the lander on a Xiphos Q7, and actually test the system in orbit around the moon in March. And the goal of this one was really kind of tackling this flight heritage challenge for deep learning models and workflows like this. So hopefully that gives you a bit of an idea of the perspective I'll be bringing to the panel. And thank you very much for having me here today.
Great, thank you. Cam, how about a few words about yourself?
Sure. My name is Cam Dickinson. I'm an engineer at a firm called MDA. So we're also based in Canada, in Toronto. And our big claim to fame is the robotic arms that were on the shuttle, the ISS, and soon to be the Gateway Lunar Station. So my background is more in sort of cameras and LiDAR sensors, but I've also worked a fair bit in developing the autonomy for the Gateway robotic system that's currently being developed, and which, when it comes online, will hopefully have a really high level of autonomy for allowing the robotics element to kind of do its own thing without, eventually without very much human interaction. So yeah, thanks for having me today.
Great. So we have a bunch of questions we were prepared for the panelists. So, but if you're not a panelist and you have specific questions that you have for them, please add them to the slider that Danielle has added to the chat. So, so before we get to just figure out what exactly, how do we solve specific challenges, we want to know where are we, right? So, in your opinions, what are the the state of the art technologies that we have terrestrially in autonomy that we should really try and develop and apply that on the moon and figure out what these challenges might be. So I'll start with Cam, since you were the last time. I'll let you be the first this time.
Okay, I would have to say that right now, things like driverless cars are probably at the forefront. There has been some setbacks, but you look at companies like Waymo, they now have driverless taxis operating in Phoenix and San Francisco. No driver. That's a huge leap forward in terms of autonomy, being deployed like in an urban environment. So lots of people around, lots of obstacles to avoid, and so far, they've been mostly successful in their developments.
Okay, Julia, what do you think?
Sure. I mean, self-driving cars was also one of the first examples that came to mind when I was thinking about this question. But another one to add that I think would be particularly relevant to this community and is a little obvious is just the construction and mining industry and the groups who are working on things like autonomous mining trucks and autonomous excavators and vehicles like that. I know I've been working with a group that's focused on terrestrial mining, and they're trying to make their truck be autonomous. And it's pretty high stakes, right? A little bit less maybe than sending something to a different planet and really wanting to make sure it works right the first time. But they also have a lot of really, big safety concerns. These trucks are massive, and there's a lot of people on the site to be careful around, of course. So I think some of the work that they're doing, and they're starting to get into the R&D space and put some of these algorithms actually on trucks and see it in operation, and looking at what they do next to do V&V in particular for those systems and make sure that they can actually become part of the working ecosystem, I think will be a good place to look for lunar applications in the future.
Okay. Becca, what do you think?
Yeah, I think both Cam and Julia hit the nail on the head. And I think that some of the most obvious translations of terrestrial to lunar are going to be autonomous vehicles and mining operations, things like that. The only other ones that come to mind for me are just kind of computer vision systems in general. It's what we're seeing in manufacturing and in medical science. I guess the other one, which we're all probably familiar with, is the language models. So things like ChatGPT, enhanced writing and search bots. I don't know if we'll see anything like that on Gateway, for example, but maybe. And then the other one that one of my colleagues always likes to remind me of is that we still have classical algorithms that are absolutely state-of-the-art in some situations, with Kalman filter being the obvious example. So, yeah, that's the other perspective.
Yeah, so it's interesting that you brought up, all of you brought up self-driving cars, but there's a level of risk associated with these systems, right? So how much are we willing to, apply these technologies on the moon, given risk. Having them on the roads and on Earth, you have pedestrians, but having them on the moon, you don't actually have roads, right? So what about the risk or unknowns with the varying levels of autonomy that are needed for the moon that might make this especially challenging? I'll start with you, Becca.
Sure. So I guess my perspective, I have more experience with the ML and the data-driven side of things. And the biggest risk there, I think, versus other types of robotic automated systems is the lack of understanding around exactly, what that system is doing and how to predict it. It is a stochastic algorithm by nature. And so that's going to have more risks involved. And I think currently our approach is to apply those to non-mission critical applications. But they are state of the art in especially a lot of computer vision scenarios. So it would be great to see those advances going into more critical applications. And I think we still need some advances there in understanding the models, in kind of the V&V aspects that I think we've had great discussions on in this workshop already. And you've kind of highlighted it in your question, but if we have more infrastructure in place, some kind of analog to roads, different comms and monitoring systems, then we can cut down on a lot of that risk. So I'll start with that.
Okay. All right. What about you, Kim? What do you think?
Yeah, I think there's a couple of things to consider in these sorts of activities. So one is if we have them operating kind of, we start them going, they seem to be working out quite pretty well. That a lot of the human operators are going to kind of get complacent and sort of that they're going to be a little bit over trusting of the algorithms. So as they're being deployed, everything looks fine, but then we might not have hit some sort of edge case that's it's an unstructured environment on the moon. So suddenly it comes across something that it really didn't expect, and it's so having putting things in place to make sure that that's being checked, I think would be one example. Another one is just if you have sort of systems that have much higher levels of autonomy, like a complete system is operating by itself, you really need to have a second system, like a second set of eyes overlooking the first system. And then you have this Russian nesting doll effect of systems monitoring systems, where everybody's kind of looking over each other's shoulder, which is probably the right approach. I mean, humans do this as well during operations, so why wouldn't we have the autonomy elements do that as well?
Julia, do you have
I guess
to add to that?
I've been thinking very along the same lines as the other two here, like how Cam just mentioned edge cases in his first point there. That was one of the first things that came to mind. Even if you're using one of those, like Becca mentioned, those tried and true types of methods for making these systems operate, you're still operating in a space where there are so many possible scenarios you could be trying to cover. And the more complex your autonomy gets, the more scenarios you're going to have to account for. So I think just having a way to manage all of that complexity and have those different levels of design abstraction helps as you're going through and developing those algorithms. Kind of similarly to what the other Julia had mentioned in an earlier presentation about balancing the levels of fidelity for when they're doing V&V for gateways autonomy.
Mm-hmm. Yeah. So so some of this had, with the risk and the models and all of these complex scenarios, it would require, particularly I think this for Becca's expertise, is that you would have to need a lot of data and a lot of experience for your system to learn how to deal with the complex scenarios. How do we start to even begin to solve that, to have the data, to have the imagination to think of every single scenario that might be needed for the Russian nested doll of autonomous systems to try to figure out what the problems are and where they are and how to solve them every time? Any thoughts on?
Maybe I can take part of this first. Okay. So specifically the data side of things, I think actually in this workshop, this has come up a lot, like how beneficial it would be if we had kind of a shared database system for, I think, both analog and simulated and, actually from space data sets that people can use for testing and training and all of these things. Like, I think unlike on the terrestrial side, where we really do have so much data, like there's such a data explosion, we really don't have that on like the planetary surface yet. So in our experience of like training that MoonNet model, we're using the 1 or 2 data sets that are publicly available out there. And then we are, going through the process of creating these analog environments. We've really got like people shaping craters to try to boost that, but still it's like nowhere near the amount of data that you want for training or for, as you importantly pointed out, testing these systems. So something like a shared database, I think could go a long way to helping us accelerate gathering that data that we need for these risks.
I think one of the other challenges is just that the data that we do have. I'll use the ISS example where we put a lot of effort into planning things to make it go right. So if you look at the data set for I'll use the example of the robotics on station, it's something 99.99% of the time it went exactly as expected. And so there's not that many actual data cases for things going poorly, which is one of the things that a lot of the autonomy, the modern, like the AI-driven solutions kind of look for. I really like Becca's comment about sort of common data sets as well. I'd also echo that it's just having sort of a set to start from where everyone can have sort of and learn from and sort of pool the data literally so that everyone has access to it and can kind of take from that. And then just one final point back to the nesting dolls. I think having these systems, they really have to almost be designed what I would call orthogonally. You have one system that's it's just set up to make sure that the second one doesn't go out of bounds. For example, it's not looking at, it doesn't care what it does, it just makes sure that it doesn't go out of bounds, rather than really caring about, is it, quote, doing the right thing? You just want to make sure it's not going to do the harmful thing. So,
yeah.
I also think the bringing up the conversation about shared data sets kind of leads us to a theme of how can we better collaborate too. And I think this is an opportunity where really government or academia and industry can kind of encourage each other and hopefully share. Like maybe there's ways government can encourage sharing of public data sets as part of certain programs or requirements, right? Depending on if that's possible or like I know we've been working with a group at Stanford, for example, on trying to get a public data set published of satellite imagery for spacecraft pose estimation. So not quite lunar surface, but just trying to get more space data out there that is shareable and open and usable by all.
Yeah. So Julia, you just mentioned about collaboration. So this reminds me of it in the networking session we just had. We were in our room. We were talking about how there might be a sort of a share architecture that is sort of like internet for that people can plug in different modules and build and add to a digital twin. Do you think that any of you think that is feasible, and how that might work with sort of collaboration in terms of developing autonomous systems? What do you think?
It definitely sounds complicated, right? Just because there's so many different types of systems out there. And I think getting things to play and talk nice to one another is one of the general challenges with autonomy. But I have seen some similar things pop up I was actually at a very similar forum like this a couple months ago, but more terrestrial ground autonomous off-road vehicle focused, like picture Army type vehicles. And they have been working on kind of a shared framework where they have this like common simulator and people can plug in their individual components and see how their algorithm works in the simulator. So I do see things like that popping up, but the begs question of who manages something like that and how do you maintain it and all other sorts.
I think that would be a great niche though for groups like LSIC or /NASA to fill, where you don't really have to define the entire system, but just defining how one piece will talk to another piece, and you're basically defining the Lego block structure and just how they click together, and that's about it. And I think, once you have that, it's very easy to build off of each other's ideas. You can take a JPL rover and click on an arm and use MCSS algorithms to run it. Like that would be amazing to have that sort of level of modularity to be able to design out and just try things. And then once you start trying them out, you're obviously learning, but you're also learning to kind of collaborate and work together and building up these systems. And things will come up that would naturally come up if you were doing it with actual hardware, just the same. And so you're actually solving hardware issues all at the same time, which I think would be fantastic.
Becca, do you have anything to add to that?
I think I agree wholeheartedly with both Julie and Cam. It would be amazing to have something like that, some kind of shared simulation environment where we can all come together and collaborate and test. I think as Cam was saying, like that's some of the best testing. There's such great testing opportunities there. You learn a lot from having to integrate with other people's components and also having other people try out your work. I think that's the most common place that we learn all of our big lessons. If someone from a totally different field, maybe different country, definitely different organization that just uses your work in a totally unexpected way. But I think Julia's right that it's a huge undertaking. So whoever decides to be the hero in this situation and take on that management should definitely have a lot of funding support and that sort of thing.
Yeah, definitely. It would be a lot of work, right, to curate the data to interface. So I'm going to move to a question that is on the Slido. So related to this question, this panel mentioned common data sets for training. What about common physics models for terrain interactions, particle, lunar physics, etc.? Everybody has their own models. Are we going to be playing nicely and say, yeah, everybody can have this? I'll start with you, Cam. You're nodding. So
I think this would be, I see this a bit as a double-edged sword, because I think what would be fantastic is the commonality so that people can compare apples to apples. I use this terrain physics model and I got these results and somebody else did the same thing. It does, I guess, lend itself a little bit to if that physics model isn't quite correct, then we've all got the wrong answer. So having sort of multiple and it's kind of like the lunar simulants. Like nobody nails the new lunar simulants with one simulant, and you buy one that's mechanically relevant and another that's optically relevant. It's going to be the same thing here, where I think you'll have an algorithm that probably does pretty well mechanically, maybe, but maybe not. The physics isn't quite, it doesn't capture everything, right? So having multiple competing models, I think, would be fantastic. But again, if it's open source, then everyone's able to use those physics models to compare to one another. So which would be that'd be absolutely amazing. So
yeah, I agree. Oh,
go ahead, please.
I run into a lot of situations where people, especially just being at a software company, where people just really want to understand exactly how all these different models work and the exact math and like even the code that's being used behind the scenes, right? So that they can build their own trust in it. So I think that's the puzzle that comes along with sharing some of those models, especially things like physics models that can be really involved, right? But if we can be open about how these are all working and able to share it and have different options for modeling different types of things, I think that helps move us all forward.
Are you worried about sort of the validation of these individual models? How they're models, right? So there has to be a way to think about how do you V&V these things? I think, Becca, do you have anything to say about that, since
Sure. I mean, I think mostly in the last points, I really just agreed with everything Cam and Julia said. Those are great points. From my perspective, I don't think V&V of models is that different to V&V of software in general. You define your system requirements, you try to come up with a bunch of edge cases and do your best to thoroughly test it and understand exactly how it's going to behave in your mission. I think my only other point I would throw in is that for models, something like this shared simulation environment would be like a great place for model sharing, for physics model sharing. You could imagine like basically being able to plug different people's physics models in, like that would be very advanced. But what a great way to learn about what the differences actually are, while still maintaining that diversity. We're not just agreeing in our simulator, we're going to use only this physics model, and now all of our tests are contingent on the assumptions of that model.
Yeah,
those are the only thoughts I had.
But also having a central repository too, like groups are going to trial it out, and then they're actually going to test it against whether it's actually on the moon or again a simulant or even something more representative, and then give feedback to the community as a whole. Like, well, this really nailed this aspect of it, but man, it totally got this other part wrong. And then, you know, we all learn together, right? And then the models that are being deployed are better fidelity or better, like they're closer to the mark than we would otherwise get if they're all in isolation. So.
Mm-hmm. Julia, do you have anything to add to what Cam and Becca have already said on that point?
No, I think they've totally covered it.
Okay. So next question that we had prepared for you is, within the scope of your particular expertise, are there general methodologies and approaches to addressing your own challenges in your development and your work? Julia? Oh.
Sure, I can start. And this kind of gets back at one of the comments I had made earlier too, where I think one of the challenges in this space is just having to deal with multiple levels of abstraction. Like if you're the person developing a certain algorithm, you have to be intimately familiar with how everything works, right? But you also still have to be able to boil that up to a level where the people from different domains can understand what your algorithm does and how to interface with it, and ideally how to bring it into a system level simulation, right? So something that I just see people have challenges with in general is managing those levels of abstraction, both like, you know, technically in simulation environments and code, and also even communicating it. So yeah, having that collaborative development environment where you could do this plug and play and see how all these different things play together would be great. And I think it helps with that communication.
Mm-hmm. Becca?
Yeah, I think one thing that's kind of a nice follow-up on what Julia was saying, that I find a regular challenge, but also like a key method in my work, is doing this switch of getting into the mindset of the algorithm. And this really comes from like defining your inputs, like what sensors are you going to need, what metrics, what loss functions are going to be the right thing for the algorithm to learn and for the algorithm to interpret. And those are often different from even the metrics that the human who is training or developing the algorithm is going to interpret most easily. So there's like that side of getting into the mind of the machine. And then there's the other side, which is like when you're defining the outputs, getting into the mind of the users, which is, you know, completely different from that other side of things. And rarely does your, you know, raw algorithm output, rarely do you want to actually show that to any user. But figuring out the right way to do that, I think in general takes just so much testing with your users. And so that's probably the other main methodology that we find helpful, like having your scientists and your operators giving feedback all the way at the data set generation stage when you're constructing like class schema, metrics and loss functions, the outputs, and then like your timing constraints. Yeah, just not making assumptions on what's going to work for them. Especially sometimes they do want the raw outputs. So that's an assumption that occasionally gets violated by especially the scientist people. Really like, look,
we like data, so
yeah, exactly.
We always like all the output. I don't care. Just give me all the numbers.
Yeah, and I think the only other thing is it's just similar to the rest of software development. Trying to keep things modular, trying to do things in this sort of iterative, cycle-based, agile development. And that's especially important with data-driven models where you really need to like generate data over and over and over again as you understand your problem space better. Yeah.
Okay. Cam?
Yeah, I'll just kind of riff a little bit off of what Becca and Julia are saying. And one of the other things we've found is that there's kind of a healthy amount of skepticism in the space community about some of the algorithms that are being developed. And it's kind of, fair, like we've done other things that have worked for so long, why would we want to change? But I think as part of this, like what we're talking about with the verification steps and testing and testing and testing and testing is building that trust up to say this algorithm's been tested by 12 different groups and it's been compared to actual data. And so that really lends a lot of credit to that, the fact that it's probably pretty close. And then there's things like building in elements into the system, like the deployment of it, like where maybe you don't go for full autonomy on step one, you kind of build it up slowly and you kind of go, the first time we're gonna crawl, and then we'll stand a little bit, and then we'll try walking before we start running a marathon. And just sort of building up people's confidence in it, I think, is a huge element to deploying these systems and getting people's buy-in across the board, because it would be a very bad day if suddenly some robotic element goes completely loopy on the surface of the moon, and worst case causes some sort of damage to another system that's there. So
yeah. So what you just said goes back to what we said earlier about figuring out like all the different scenarios and be prepared for them. And so we have a question on the Slido that says, is trying to find a complete cover of scenarios really practical? How do we plan for graceful failure? How would you do that?
So I think this goes back to the Russian nesting doll thing that I was talking about before, where you're never going to, within a single system, make it completely bulletproof. Even without the use of artificial intelligence, it's very hard to kind of design for every single contingency that's going to take place. If you do have high levels of autonomy, though, having these alternate systems that are completely separate, there's no, they have a whole other set of sensors, they may have been designed by a whole different team, and yet they look over the shoulder of the first one, and there you're able to sort of really cut down on the chances of anything going completely outside of the box, because the second design system is, as I mentioned before, maybe one that's just looking at to make sure that you don't go out of bounds, and that's all it does. So it might be a bit more simple, but it has a high impact, like it's trying to reduce the impact of the first system if it were to start coloring outside the lines.
Mm-hmm. Julia, do you have anything to add to that question?
I mean, that was spot on in my opinion. The only other thing, I'd like this question. I was actually, the other day I was talking to a coworker about something similar, but more through the context of like, where would we see AI get applied in these applications first, like really get deployed? And he had brought up the point that maybe it's situations where, we have a certain algorithm and we get into some kind of operating region where our MO is do nothing. Like we can't move anymore, right? We lost comms, whatever it might be. Maybe in some of those cases, actually trying out the AI algorithm might be better than doing nothing. You don't miss a science opportunity or whatever it might be in that case. So yeah, maybe that kind of gets into the graceful failure part of it, I think, here. And yeah, I don't think covering all the scenarios is practical. There's always going to be something that you can't account for and you don't know until after the fact. Hindsight's 20/20, right?
Yes, definitely. Becca, do you have any additions?
I think they covered it pretty well. I think the highlights are, redundancy of supervision, and then also this decoupling aspect. You want to be able to disengage your autonomous system if it's not working the way you want it to be working. And this idea of kind of like opportunistic autonomy that Julia mentioned, I think is a great stepping stone until we have some of these technologies a little bit more figured out.
Yeah. Okay. So another question on Slido is, earlier we talked about huge, data center on the moon. So the question is, considering signal issues, would the data storage be located on Earth or on an orbiting satellite? I guess the corollary to this is that how would we transfer the data back on Earth to inform more models. So Becca, I'll give this to you first.
This is a really good question, and one I definitely don't know the answer to. It's I don't have a lot of comms experience. I've tried to think about this problem a little bit in some of our recent work. So there's a bunch of different approaches. I think maybe Cam or Julia might have more to say here, but the kinds of things I've thought about is this kind of downlink prioritization aspect. And that's often a place autonomy can come in. So just being more selective about what you are downlinking. I think also the closer you can have your database to your asset, the better. With that kind of trade-off of, the different environmental effects and the cost of getting it up there and all of that stuff. I think it would be pretty cool to have, let's say, an orbiting database around the moon that is maybe also like kind of orbiting extra compute processing. But whether or not that makes sense, I think I'll leave to somebody else.
Okay, Julia, I'll punt that over to you.
Oh, I'm not the expert on this one when it gets into space comms, and I was hoping for Becca or Cam to have some good ideas, and I liked a lot of Becca's that she mentioned, so I'll punt it over to Cam.
I think the term is edge AI, where it's kind of like the deployed element is right at the business end of what you're taking on, and there, besides the having, like, one of the major hurdles right now is just having the compute power at that location. Like it's very hard to get high-end computers or GPUs into space to actually deploy it. So there are different things you can do as well, like skinnying it down and sort of, or dumbing down sort of the algorithm or what you're doing. And this is just by necessity. You have to kind of make things a bit more simplistic. Or your database, it's, although it's being housed there, it's really not collecting the same, like you're filtering out the data, you're triaging the data quite a bit of what you're going to save. And there's risks to that. I mean, one thing that these AI algorithms do really well is with very rich data sets, they're able to tease out a lot of different things. So you'd kind of have to give up on some of those sort of those edge cases being caught. And again, it goes back to, it's sort of like an overall architecture discussion about, do you, can you have kind of a simpler AI element right at the focal point, right at where you're the business end? And maybe it's not as bulletproof, it still gets the job done. And then you just live with the fact that maybe some of the times it's going to make a wrong step and you'll just catch it and stop it and say, okay, I'm going to now revector you in a new direction, and we'll try again. So I think having, it'll take time for the hardware to catch up, and then in the meantime it will probably be a bit of a stepwise sort of learning curve, and I think we just have to be a bit more forgiving in terms of these algorithms being perfect, which is hard to do. In space, determinism is everything. Like that is the penultimate for development in space. Just knowing exactly what your system is at every point. Like that's what everybody strives for. It's probably just not going to be possible for some of these elements, and you have to kind of learn to work with that or work around that. So.
Okay. So we have less than 3 minutes left, and I want to, give each of you a little bit less than a minute to sort of give us some final words about what you think about, challenges and how we might, particularly for our interests is sort of applications on the moon or other planetary bodies, and how your wisdom on how we might start solving some of these challenges. So I'll go again with the order that I have on the slide is I'll start with Julia and then Becca and then Cam.
Yeah, sure. So I can speak from a little bit of the experience I have working with people working on terrestrial mining, but I think a big thing I see there, it's kind of like Danielle said earlier, you can't just copy paste from Moon to Mars. That group has the problem of, I can't just copy paste from autonomous cars to a mining environment. And like for all of you, you can't just copy paste from terrestrial applications to something that works well on the moon, right? So I think that's one of the biggest challenges. Like for example, one of my coworkers made a really detailed model of an excavator, right? In one of our dynamic modeling tools. You can change gravity in that tool, but I can't just go and be like, oh, let me put moon gravity in this tool and expect it to start working, right? There's so many other factors to take into account. So I think that's some of the biggest challenges. We have this perception of how something works based on our experience on Earth and seeing these excavators and different construction equipment work, right? But then how that actually works on the moon might look entirely different. So that's one that I see.
Okay. Becca?
Okay. There's a few things I wanted to cover. Kind of going off of the discussions that we've had in this workshop, and what Cam was actually just talking about, identifying where we can start introducing autonomous systems, where it's acceptable that their performance is a little lower than what we would expect from, a fully human-driven deterministic system. Identifying those applications, and then going for it, ideally with new standards of V&V and quantifying these levels of uncertainty, and building in extra redundancy. And I think some of the other sessions in this workshop, for instance, maybe swarms are a great way to start building in redundancy that makes it easier to add these more complex autonomous algorithms. I think from a technical perspective, in our work, we're really hoping that there's going to be a bunch of advances in like continual learning, this kind of like online learning field, because if we can unlock that for onboard autonomy, that's going to be the game changer. We don't have to worry about this data storing problem that we've been talking about. But in the meantime, coming up with clever ways to do like model serving and model updates, because we are going to want these systems to adapt and refresh, is I think a big need. And yeah, I think those are kind of my wish list of the things to come next. And I think in space, people are always innovating, and those innovations get returned to terrestrial. And I think these autonomous algorithms are another example. We can see that happening. Maybe we can unlock the secrets of the lightweight neural network algorithms and transformers and that kind of thing. And make it work for our more extreme environments.
Great. Cam, you get the last word.
Great, thanks. I would actually just echo both what Julia and Becca said, and in particular with what Becca was just talking about. I think one thing that I could see that would be really helpful is kind of like a graduation system for a particular element, not so dissimilar to the TRL kind of classifications, where you have an element that's deployed for the first time, and you give it all the bandwidth, and you're just collecting all the data, and you're monitoring it, and then and it's a complete system with an overview checker and stuff like that, and you're just making sure that it runs for 100 hours kind of without any exceptions. And then once it graduates from that, then maybe the bandwidth gets turned down and you can focus on other elements, but you're still monitoring it with maybe higher, like spot monitoring or something like that. And eventually it gets to and if you want like an ARL or something where it's high enough that it basically has proven itself worthy, and you can kind of it's all of it's understood in terms of it's thought that all the edge cases have been found, and that the system that's overseeing it is responsive enough that it's not going to kind of cause any sort of spurious behavior. I think something like that, and defining that, this forum would be a fantastic kind of body to do that, where we can talk about like they have this already for the classifications for AI autonomy, like on cars and stuff like that, but it's not so dissimilar classification system or graduation system, I think would be really super helpful.
Okay, great. Thank you. We're out of time, so I appreciate our panel for taking the time to talk to us. And I think we have a quick break until 2:45, and there's a new poll. So please go take it, and we'll come back after getting our coffee. So thank you again for participating.
Thank you.
Thanks.
Okay. I guess we'll give a
Hey,
hi.
yes, in answer to your question. So yeah, welcome back, everyone. Hope your coffee was just as good as the last 5 breaks. And we'll get started on presentations. Stacy, after you.
All right. All right, everybody. So our next presenter is Casas Alexis. Casas, are you here online?
Yes, I'm here.
Great. So are you sharing slides or are we? Sorry about that.
I will be sharing my slides myself now that you just started. So you should be able to see my slides now, right?
Yes, perfect. So Casa is from the Norwegian University of Science and Technology, and he's gonna be presenting on Brazilian robotic autonomy methods and systems. So please take it away.
Thank you. Thanks for the invitation. And I have been excited attending the discussion so far. I learned a lot of challenges I should know, but I was not aware at the moment, also in a very important perspective about how difficult it is to establish resilient autonomy in my words, on the moon. But let me just go directly with a video to motivate what I will be talking about in this presentation as briefly as possible. So we have done quite some work from a research perspective on enabling robots to operate with resilience in diverse environments, especially underground, but also in other industrial and natural environments. And the video mashup that you see here is instances from such results where you see drones or walking robots navigating and exploring and mapping relevant underground environments. Now, I have tried to express collectively what we are trying to achieve in terms of autonomy. And we try to say that we try to make sure that the system can retain performance, even in the presence of unexpected phenomena, disturbance, and so on and so forth, right? And to establish such resilience, we say that our method should present the 3 virtues of redundancy, resourcefulness, and robustness, and therefore have essentially their ability to respond and recover from failure or potential failure. And I will just focus on 3 directions of research in my group that I believe are also relevant to the discussion today. The first is about the ability to perceive through degradation. In other words, it is very, it's quite established at the moment. And there were many comments before in the panels, for example, about how computer vision has progressed majorly. At the same time, it is way more difficult to make sure that there is no point of failure for a robotic system. If we take the localization and mapping problem as a case, then it's very difficult to make sure that we can ensure such reliable operation in not only GPS-denied environments or dark, but also with obscurance, smoke, dust, and so on and so forth, geometric self-similarity, etc. So we have a line of activities in my group that relates to multimodal fusion of diverse sensors, in particular sensors that allow to penetrate such conditions separately with LiDAR for good geometry, areas, thermal vision to penetrate through obscurance, and so on and so forth. And the whole operation relies on the fusion through the use of factographs, nonlinear factographs. And this allows us to integrate diverse modalities and solve one common optimization problem that fuses the constraints now just depicted as a visualization there as a factor on the Markov process. And we allows us to combine constraints from relevant sensors, different sensors, into one single optimization problem. And the benefit of this is that if we can provide the terms not only in their additive sense, but if we can also manage to explicitly detect when each modality faces a failure, for example, in a self-similar tunnel, LiDAR is expected to fail, and then we know that we can put more weight or solely rely on all the other modalities. And we call this handling degeneracy, which means that we know that the sensor is failing, we identify it, we try to do the best to get them as many degrees of freedom as constraints from said sensor, but otherwise rely on the fusion of different modalities. And I refer to exteroceptive modalities here, meaning especially in our work, LiDAR, vision, long-wave infrared, and those are combined afterwards with program reception with IMU. Currently, we also work on radar sensors for similar cases, but different environments. And we have also the case of handling long-term degeneracy by means of a robot that has certain sensors that have failed over several minutes or more, but once those also recover, it managed to bring again a multimodal map that then subsequent phases of the operation register those. Now we have several results in this direction. On the left, you see, well, you see the data, but it was a walking robot that navigates down a self-similar tunnel and then inside the mine, and then coming back. And previous method of ours makes a drift error, whereas the new method, of course, makes this correctly, right, by correctly identifying the degeneracy and attaching only the associated constraints. On the right, you see on the up a robot that flies through a smoke-filled underground mine, and on the bottom a more like toy scenario with a perfectly self-similar man-made tunnel. Now, if we have the ability to penetrate condition degradation perception-wise, the second major line of work that we do is on autonomous exploration or coverage path planning or any other means of information sampling. And to that end, it is key that we try to focus on methods that provide scalability, and I will connect afterwards with the DARPA Subterranean Challenge, meaning methods that can operate over several kilometers of emission, because it is obvious that we have very high performance in small environments by dense sampling, for example, in graphs or trees, but that's not the case, of course, as environments grow. So it's important to have an architecture that allows to retain computational performance over large-scale environments, and we do so through bifurcation of local and global stages, with in the local stage also honoring all constraints that relate to terrain, for example, for ground systems, traversability, limitations, if a certain soil is actually passable, if it's, you know, a water puddle or actual solid soil, and so on and so forth. And you can see results of this line of work, both underground on the left, but also in industrial environments, as you can see on the top right video with a drone flying inside the ballast tank, meaning on the sides of a vessel, maritime vessel. On the left, animal is just exploring a lot of, actually it was 37-minute autonomous mission where it does a large-scale exploration process. It finds several dead ends, but it remembers to go back into previous intersections and continue the exploration, right? So it's an autonomous functionality that negotiates large areas without the need of any human intervention. Likewise, on the drone video on the bottom right. Now, in our experience, despite this line of work from our side, but also the general work of the community and excellent contributions, it is very difficult to always come with a hard claim that my localization method, for example, my perception, my mapping, will never fail. And it is unfortunate, however, it's a fact that currently the state of the art in autonomy relies on this assumption that there is a good position estimate and a map one way or the other that happens in real time. And we want to alleviate this constraint, not to say that we don't want to run mapping in several states, associated state estimation in real time, but we also want to say that even if this fails, we want a control methodology that allows us to go to a destination, even in the absence of a map and in the absence of a position estimate that is reliable. To that end, we developed or we replaced essentially traditional position controllers with a learned navigation method that has three distinct features. The first is that it uses only a partial state, meaning only up to the velocities of the road. So roll pitch, for example, for a drone, and linear velocities alongside angular rate, yaw rate. The second, it uses the depth image, either, you know, two stereo images, for example, and reconstructing depth, or directly a depth image from any depth sensor. And then it also focuses on noise on this depth sensor and uncertainty on the partial estimate. Focusing on these distinct features, it builds a pipeline that exploits a deep ensemble of neural networks in order to deal with epistemic uncertainty related to the noise on the depth image, and the uncertainty transform to deal with aleatoric uncertainty, meaning the covariance over the partial state. By sampling multiple sigma points over the covariance of the partial state and feeding them through the neural network, it allows to account for the covariance over the partial state, and therefore it allows to be uncertainty aware in its estimation if a certain action, meaning how to go to the destination, shall be collision-free or not. By running not a single instance of this collision prediction network that I marked there as CPN, but running essentially a sequence, an ensemble of these collision prediction networks for each candidate prediction of a possible action, it allows to deal with several variations or alterations of the amount of noise a depth image shall contain. And if you focus on the image on the top right, you will see that when we navigate, for example, inside the forest, it's so difficult to have accurate depth data because several of the branches might be 1 or 2 centimeters thick, and it's just, you know, simply difficult from stereo vision to have reliable reconstruction of depth at this point. Same thing with other surfaces, such as, for example, reflective surfaces and so on. So we have paid attention into creating a methodology that assesses if a list of motion primitives, candidate action sequence, shall be in collision with the environment or not only in the sense of ideal data or a little bit of noise, but extensively taking into account depth image noise through the epistemic handling via the deep ensemble, so a sequence of neural networks, and also aleatoric noise, essentially the covariance of the partial state. And the methodology, as mentioned, does not rely on assuming access to a map or a position estimate. Last but not least, on the same method, we have also attached the ability to look towards areas of interest, but that's something that maybe it's not part of special importance in this discussion. So if we look on this video now, on the left, this drone will fly to the destination being now a direction vector from a high-level planner, but the avoidance of the obstacles and the overall navigation that you see does not utilize access to position estimate or the map of the environment. And again, I highlight this not to say that we should not be running SLAM, and according to the previous line of work, it's not relevant. It is to say that we have a second layer of resourcefulness, of redundancy, such that the method enables the system to keep operating safely, even when, for example, SLAM might be broken for 1 or 2 minutes and before it recovers. So this way of thinking is something that we put in test, not the latter work, which was developed later, but the works up to the previous topic. We put on the test through the Dataset Training Challenge, which was an activity that finished in September 2021. I had the opportunity to lead a team called Cerberus. I'm with myself, and Cerberus is the mythological creature that protected the underworld. That consists of multiple universities. Let me just honor my partners. I was at University of Nevada before, and then I moved to NTNU. And then we had also ETH, Berkeley, Oxford, Reliability, and Sierra Nevada Corporation as part of the group.
Costas, about 1 minute.
Yes, I'm actually done in a minute. And we had a set of systems deployed in the competition, and the results that you see essentially are instances of the last 60-minute mission that we deployed multiple robots, and we managed to explore in total 1.3 kilometers through the underground environment, which I believe is essentially relevant to the topic of discussion today, right? So long-term, or at least in my view, for now, let's say long-term autonomy without any teleoperation whatsoever through this process, and finding also objects in this exploration with accuracy of no worse than 5 meters over this approximately 1.5 kilometers of exploration. That's actually the last thing I want to say, and I want to highlight that we have open source a lot of the work that I mentioned, and it's available if others have interest.
Okay, thank you. We will wait until the end for questions and answers. So we'll have our next speaker, who is Craig Knuth from the Johns Hopkins Applied Physics Lab on challenges in developing advanced autonomous navigation for the moon. So Craig, I think I saw you earlier. So
I'm right here, yes.
Online. Great. So are you able to share your slides or?
I think Christina is going to share on my behalf.
Great. Christina?
Getting there.
Thank you. I know.
Thank you. Let's see. We should be ready in just 1 second. Uploading. And share screen. Here we go.
Thank you. See them.
Great, thank you.
All right. Craig, all yours.
All right, thank you. Hi, everyone. I'm Craig Knuth. I'm with the APL. I broadly work in the areas of robotics, machine learning, safety, and lunar navigation. Next slide. So when we talk about what we're looking for in terms of navigation for the moon, it's really quite a bit different context from, I think, previous space missions. In fact, in the way that this is going to be sustained lunar operations on the surface of the moon. And there's going to be a large need for both transporting materials and also navigating to unknown areas, new areas to conduct science. And whatever navigation solution we end up having is going to need to be not only robust and long lasting, but it's also going to be able to be needed to reconfigure and adapt to new tasking and new missions as we continue our presence. And right now, I think there's a few different ways in which existing space rovers are designed with a little bit of a different tint than what we will need for the lunar surface. One is that previous missions are designed with extremely limited risk, right? If your rover breaks down, there's no way to recover it. But with the sustained presence, we do have recovery options available. And so there's a little bit more risk tolerance. We can take a little bit more aggressive actions in order to get better mission performance. Secondly, right now, rovers are designed with a lot of human guidance, and that's just not going to be feasible to be able to do traverse on the moon at speed well a human is in the loop throughout that traversal. And furthermore, as I mentioned already, but previous missions are about one specific mission or is designed for a task or a suite of tasks, but is never reconfigured or readapted in a significant manner for new efforts. Next slide. So in terms of producing kind of a robust and capable mobility solution for the moon, I think it's going to involve a lot of different types of mobility. Here's a suite of different rovers and robots that have designed according to different environments, some more space qualified than others. But I think ultimately this heterogeneous team that can be readapted in order to be assigned to a particular task is going to be key to providing efficient and effective navigations for a variety of tasks on the moon. Next. So I'm going to talk briefly about a few different challenges to achieving this navigation for this heterogeneous suite of robots. This has been talked about throughout this autonomy workshop, so I'll just try to keep it brief, but I do want to go over each of these in turn. Of course, the environment itself is really abrasive. Dust is really abrasive. It can hide certain objects on the moon, rocks, and that may damage the rover. The regolith that we drive over may be loose. We can slip down hills. We can crush regolith and end up with stuck wheels. Beyond just the surface characteristics, there's lots of challenging lighting conditions. Lunar dust is very reflective and presents a very unintuitive viewpoint for human beings, and we don't want to also have our robots carry that same human bias. And in addition to lighting challenges, there's really extreme areas on the moon, permanently shadowed regions, crater walls, pits and skylights that we need to be able to navigate around and through. Next slide. Beyond specifically challenges for navigation specifically, there's lots of indirect challenges that lead to difficulty in navigating. One would be unreliable comms. If we lose comms or reliable comms to a lunar base or to a satellite, how do we reestablish that as we're traveling through the environment? We need to be able to have a way of robustly reestablishing comms if we ever lose them. Of course, we don't have GPS, so we need to handle localizing or at least knowing where to go in the environment. Another challenge I want to highlight is lunar night survivability. If our rovers can survive the night, that's great. But if they can't survive the night, we need to factor that into our navigation approach, where we always need to be able to return to a safe zone to be able to continue using that asset in the future. Next slide. So one way that we can really improve the navigation ability of our systems, and this is a little obvious because we're at the autonomy workshop, but of course we want to reduce human intervention. Just the moon earth latency just won't be, it's too great to really make teleoperation effective in terms of navigation, and so we need to have an autonomous system for navigation, and I think critically this will rely on some sort of risk termination, and that goes beyond just collision and slipping, but thinking about, can your wheels get stuck? Are you going to incur vehicle damage? We need to address all of these sort of characteristics of risk for our rover in order to be able to reliably plan and robustly plan through the environment. And maybe at some point we determine the risk is too great, or at least we don't know what the risk exactly is, and then we do kick it back to a human. But primarily this needs to be done autonomously. There has been some efforts to do these really long navigations on Earth. The Viking is a recent paper out on this topic that traversed over 1 kilometer, but it's going to take a whole nother level of efforts to put rovers on the moon to traverse even greater distances and without ever being able to actually test in that environment before doing the traversal. Next slide. Another critical challenge is going to be trust and assurance. Of course, as we increase our autonomy and we increase use of AI and ML, data-driven methods, how are you going to actually validate that is a huge challenge. And I think that comes out in a couple ways in terms of how are you going to establish trust with operational engineers. Somebody's going to be running this algorithm and they need to trust that it works. So however we can surface kind of the understanding of the environment from the rover and serve that up to an operational engineer so that they trust that it will navigate correctly is important to increasing the overall mission efficiency. And another important, I think, way of establishing trust is to have multiple failbacks, multiple ways of mitigating failure. And this gets to Kostas' talk just a moment ago, where you have several different layers of how do you, if something fails, you have a backup and a backup to the backup that can ultimately ensure that your system will not crash and burn, and you'll still be able to reuse it even if you need to pause on mission execution. Next slide. Another big challenge for navigation is really on Earth, we're using a lot of machine learning algorithms to get really good performance in navigating over terrain. Because of that really complicated interaction between the vehicle and the terrain itself, learned models provide a lot of ways to overcome that barrier. But of course, if we want to put this on the moon, we need to get that, we need to have data to train on, and that is a huge challenge in both in assurance and also just making sure that things will actually work in terms of if we have synthetic data, there's going to be a gap to take it into the moon. And if we test on terrestrial test environments, that's still going to be a close analog, but there's still going to be a domain shift going to the moon. Of course, this is a general problem in machine learning. How do you address the domain shift between environments? But it's an especially critical challenge for applying learned models to the lunar environment.
About 2 minutes, Craig.
Okay, thank you. And so one way of potentially reducing this data complexity, of course, is how do you isolate components of your system? We have segmentation models, and if we can rely on segmentation models and have a way of validating those for a lunar environment so that downstream they can be used in other learned models that can just rely on the existence of a quality segmentation model that can help address some of these data problems. Next slide. I think one important way to applying a heterogeneous team is how do you coordinate all of these different types of mobility? So I think another important problem to address is going to be understanding terrain affordance of different areas in the environment. Where can my hopper go? Where can my wheeled vehicle go? Where can my legged robot go? And why would I choose one robot over the other in terms of maximizing mission performance? So this optimization over this heterogeneous team, over understanding all these different terrain affordances is a really complicated problem, but I think will really go a long ways towards creating a way of adapting quickly to new tasks and missions as we come up with them with the sustained lunar presence. And with that, I'll conclude my talk.
Thank you. Thank you, Craig. So anyone with questions for Craig, please put them in the Slido. We have one last speaker, and it is Ed Brewers from the Johns Hopkins Applied Physics Lab, presenting on test and evaluation of autonomous systems. So Ed, I hope you're on. Do we see Ed here? Oh, there you are.
Oh, sorry. I might have accidentally muted you when asking you to unmute.
Okay. Good afternoon or good morning, everybody. Happy to be here. My name is Ed Browers. I'm in the APL Intelligent Combat Platform System. I spend most of my time testing various autonomous systems ranging from simple PID based all the way to complex RLML systems, usually multi-layered autonomies, so an autonomy controlling autonomy, and 99% of the time in distributed mode, so multi-systems, multi-vehicles, multi-units in play at a time. So I structured this really at a high level. So insert moon or insert any other environment relative to say typical UAS or other UGV, UUV type testing. But basically, autonomy testing kind of falls into a key set of challenges. Number one, it is easy to operate the vehicle generally, to fly or drive or do anything to get from here to there. That is a relatively easy task. I'm glossing over a lot of the nuances, but operating an entire system, so you're driving and sensing and doing this, that's where the challenges start to really pile up into an n-dimensional problem. Most autonomous systems are layered. Like I said, autonomous systems controlling other autonomous systems, and there's complex interactions there that need to be considered. And ultimately, autonomous systems are distributed. They are not all on one processor. They're not on one vehicle, not on one data bus, not on one everything. So data fusion, comms, and ultimately a system timing understanding of where they are become core challenges. So what this yields is a system of testing challenges that are unlike any other classic aerospace T&E approaches. So number one, there are very few, if any, standards. So to get approval to use an autonomous systems in a specific area on a specific system is actually very, very varied in terms of how do you go about it. Measures of performance, measure of effectiveness aren't easily defined. Usually we have a human reference for the autonomy, but often cases the human's not even involved, so there's no reference standard. There's layered approaches. We'll talk about that a little bit more later, but where a lot of our challenge usually comes is more advanced autonomies are usually non-deterministic. So when you're trying to apply it to a safety or mission critical system, and the safety officer or the safety board says, okay, what's going to happen next? And your answer is, I don't know, because I can't know because it's not deterministic. That usually stops the conversation very quickly and ultimately requires a much deeper level of approval process to get that system in service. And often achieving our ultimate goal of achieving explainable autonomy, or which goes to trust, is very, very difficult. So in short, what I did try to break this down into how we approach it here on integrated system testing. So into kind of four core bullet points here. It's really defining the use cases and ultimately risk tolerance, building T&E in from the start, hardware in a loop plan, and then the HMI. So at the top level, again, our fundamental goal is to safely test autonomous systems in a build-up fashion up to including their operational environments. So where the core goal that everybody's after is getting to a point of explainable autonomy, or explainable AI is more the buzzword, but autonomy is not just AI. And ultimately to trust. Do humans trust the system to operate effectively and safely? This has huge impacts on the T&E approach. And that starts with the type of autonomy, from is it just an aid or a replacement, through where are you in your testing phase? For example, the early testing of comparing different autonomous approaches drives setup repeatability problems. And that's very, very hard, especially for autonomies that are at the machine level precision generates different non-deterministic effects. So are you comparing autonomy to autonomy, or are you comparing starting condition to different starting condition? So there's a lot of apples and oranges you got to sort. Autonomy complexity, again, systems controlling systems, that generates a lot of thought processes that you need to be very careful about. And then ultimately risk. This could be a whole discussion in itself, but when you're talking flight critical systems or mission critical systems, depending on how you want to approach it, this really drives how you approach the autonomy system design and ultimately the artifacts that you can achieve from the testing to validate the next gate and get moving closer and closer to the ultimate operation. So basically, the use cases derive the test and evaluation approach, which ultimately drives the autonomy, and I'll explain why. In a typical approach, this is very simplified, where you have an agent that's receiving an observation space and providing actions to either sensor systems or actual vehicle controls or other articulating systems via a distributed operations framework. This is connected to some kind of human machine interface, some kind of control, and often to other systems. This fundamental construct you see in a lot of autonomous systems, but really drives a lot of the T&E approaches. So such as, where are the very clearly defined boundaries between systems? What is the timing approach? Where are the limiters on the system? How are we going to operate this thing safely within bounds? And what is your ultimately approach to deployment of how do you get autonomy onto the system? And then how do we orchestrate it such that we actually coordinate the overall system actions? Those are much bigger challenges than anyone really accepts at the beginning of an autonomous project. So where T&E can come in from the start, a very simple but very effective approach to this is adding a software-based runtime assurance in between your autonomous agent and any kind of system that impacts control or system safety. The software runtime assurance is typically monitored and has its own boundaries. This piece is of a high TRL level and validated and approved for this role. And it is basically effectively a soft kill switch in the sense that it pulls the AI away from actually controlling the system. It provides additional control injection to move the system back to a safe place and only reset for another go. That all sounds fairly straightforward, but is actually pretty hard to achieve because the key part in that statement was certified or otherwise defendable for that role. Hardware kill switches are usually added as well. These are more of a nuclear type option where once this switch is thrown, that is kind of end of test, end of that overall evolution, because either that switch is impossible to reset remotely, or is tied to a very egregious failure of the runtime assurance or otherwise parts of the system. So this is an item that needs to be considered carefully. Message transport, between this entire system, latency needs to be considered from the very start. Now, I'm typically used to high frequency operations of flight controls and systems and stuff like that. Operating at 10 to 50 hertz plus. But slower systems need to be considered in terms of latency, because comms between different pieces, latency just between messages within the system, et cetera, do have a large impact on the autonomy that may be in the system control layer, controlling the modes of this particular other agent. So the latency and there's a big part of that feedback between those two items. And finally, logging needs to be distributed throughout the system, so that way you understand which piece of information of the block diagram knows what information at what time in order to help troubleshoot what is exactly happening. In many ways, many distributed systems, there are alternate pathways for information to flow around the system, between, say, networking of different components. So this is important to the process.
About 1 minute, Ed.
Okay. For T&E, strongly suggest starting with as full of a system as possible. So this is starting with operating on the target hardware with simulated physics, simulated sensors. And only from there, you start degrading to an agent training mode, where this is fully a model and simulation representation, moving up to a slightly more complex arrangement for CI/CD type training, and then eventually bringing it over to the more block approach to the live system, where, say, just the sensor package now becomes real. But the point is, by starting here, you have a clear path between the simulated world and the live system, because you can more clearly reflect the pieces of the block diagram from a simulated world to a live component. However, the main challenge here is making sure this agent training world accurately reflects this world here in terms of latencies and other key pieces. The last piece I want to throw out is that the HMI is usually the last thing people consider. It's the bolt-on piece at the very end of the whole thing. This has an outsized role in the explainable autonomy and or trust approach to this. So this needs to be considered basically from the beginning and included in all the testing buildups. So that's the end of what I have for you.
Okay, thank you very much. So if anyone has any questions for Ed, please put them in the Slido. The link is in the chat. So we have a number of questions for at least for Costas. So Costas, the first question is, how large are the neural networks that you're using? How much data did you need for training?
Yeah, I will just answer the question primarily from the latter part, because I think the size of the neural net now is not necessarily the most relevant question. For the latter part of the work that we showed, we need 16 hours of data collection on a Threadripper. So that's a good CPU essentially, but not too much of process. And the process is that a drone is flying multiple missions in parallel, right? So we have a simulator that runs faster than real time. And we spawn multiple drones to collect such data in environments that we randomize. So eventually this means millions and millions of images, but it's actually 16 hours of training the navigation policy in these diverse environments. I think the most critical thing is that we have abstracted the process, and the depth, the processing of the depth images, which is the most high dimensional input state, is something that we pre-train, and in that we can also add real data if we want. And then there is the part that predicts collision, which is a smaller part of the neural network, which we train separately. The collective process only with sync data is 16 hours, but you can verify the first part, which is processing a neural network to process the depth data. So I can provide more information if needed, or I can post a link to the papers.
Okay, related to that, can you elaborate further on the computational needs and resources to achieve the comparable navigation and mapping performance?
So now we go to the onboard part, because the thing I mentioned before was purely the offboard, right? So the training. Now onboard, all the pipeline runs on we have tested on 2 processors. One is a CADET processor. This is essentially a 6-core ARM processor, much analogous to your standard smartphone. And this is for all the work that relates to SLAM, path planning, and control. For the work that you saw that involved deep neural networks, we run it on NVIDIA Xavier, which means essentially it is roughly a 200 grams board. And on the same board, we also run the SLAM pipeline and low-level control.
Mm-hmm. And then also people were wondering whether Cerberus could be used in emergency scenarios, like mapping safe routes during fires and finding people in collapsed buildings. I guess that's for terrestrial application.
I always don't like to promise things that we have not tested around fires and things like that. I think it's something we need to put a lot of work to make this happen, right? So I always resort in saying what we have actually achieved.
Do you plan on, I guess,
we have a new project.
We
have a new project that we start actually in September, which is about supporting emergency responders, but in a more combined human plus robot fashion. So the idea is that the robots are in the vicinity of the human first responders, and they just go forward to explore, but they're not 100% autonomous as we deployed, for example, in the Dara challenge.
Okay.
And this is exactly the last question, right? So it is about also the human-machine interface.
Yeah, so the human-machine interface, I think this one is for Ed, is do you see the human-machine interface as a shared control implementation with variable levels of abstraction and primacy?
Yes, absolutely. Where the HMI has gotten, at least in my experience, have gotten into trouble with it is just the sheer amount of information that can be provided, and at what level on the system is it being provided. So if you are interacting with one autonomous agent, to take a spacecraft for an example, you're working on trying to get just basic navigation, but the basic navigation is also influenced or tied into other sensors that feed that navigation and the modality of those sensors. That's where things can get stuck in a really precarious loop of the operator or the human, in this case, you trying to interact with one piece of the system, but that piece of the system has implicit changes to the other part of the system that the operator's not intimately aware of. And that's really the main concern is providing the appropriate situational awareness at the appropriate levels, and only providing enough control to the human that makes sense, that can be actually actionably thought of and worked through.
Okay, thank you. So I want to close out and give all our speakers a chance to answer the question. Well, actually, we have one more question, so I'll take it from the Slido. so that, I'm selfless like that. I don't get to ask my question. So for Ed, the HMI point is well taken. Sometimes autonomy developers deliver capability to a customer who later integrates its HMI. Suggestions for such cases?
Yes. So the way we've approached in the past is have a kind of effectively a standard of here is what is available on the HMI that is actually provided straight to the autonomy developers. So it almost, we flip the script in a sense that the HMI is mocked out at the very minimum, but usually in a functional state first. Then that is sent over to the autonomy developers, and then they had to work within that framework. Similarly, that also applies to the orchestration and the deployment mechanism, because I've seen many autonomies that are the best thing ever. It's great, but only works in M&S, and there's no way to port it into live systems. So they're just either too big, too memory intensive, whatever the situation may be, that they do not fit within the actual compute space or the deployment mechanism to actually get that onto the live hardware. So similarly, that is kind of predefined and then provided the autonomy framework for autonomy developers.
Okay, thank you. We're out of time, so we have another break coming up and for another poll. So if you will go to the Slido, there's another poll for you to answer. We'll come back at 3:35. So see you all, and thank you to our speakers.
All right, welcome back, everyone. I hope you didn't take us too seriously when we told you to be back by 3:35 a.m. instead of p.m. So we're coming towards the end of our second day, the end of our workshop. We're going to do one last networking discussion with our dear old friend Miro. So this time we have software challenges as one breakout and hardware challenges in another. With the help from subject matter experts, these are the rooms we got. If you would like, we'll randomly distribute everyone into rooms. If you would like to be in the opposite breakout, please come back to the main room and let Christina or myself or any of the co-hosts know, and we'll put you into the correct room. Otherwise, good luck, have fun, and we'll meet back here at 4:35. All right, welcome back, everyone. Thank you so much for all your participation. I know we had a great chat in my breakout, and I'm sure everyone else did. Thank you for adding your notes and your thoughts to the Miro boards. I wanted to mention one last time that the Miro boards will continue to be open for the next couple days. So if you have additional thoughts on the workshop and you want to add them, please go ahead and throw those in the boards, and we'll be looking at all of the comments. So if you have something you want us to take away from this, write it down. Other than that, we're gonna close out. We have day 2 closing remarks and our next steps for LSIC, and that'll be led by our own Wes Furman from Johns Hopkins Applied Physics Lab. He's our LSIC lead. So Wes, take it away.
Sure. I feel very honored that you asked me to help close out this workshop. It's been a fantastic event for me to listen into and learn a lot from all of you, and I think that's really my major takeaway is how much the broader team has to offer here. So thank you very much, Danielle, for organizing, Stacy, all of the other APLers, and all of the other presenters that came together. Right. So I really appreciate the insight that we build, the opportunities for these discussions, and that's what keeps us moving forward. And keeps us moving together, and that's really the only way that we get to the moon. So I have a couple major takeaways that I thought about, just major themes that I think I'll sort of raise them a little bit and then call on some of the other folks who are here and were deeply involved with this workshop to kind of cover those as we go through. And then I'll talk about some of the previews of things to come, and just a vision in the next couple of interesting things that are on the horizon. So first, when I looked across, when I asked the rest of the team to help me get some of these themes, the first thing that came up was definitions and what matter and why they matter. Something I think Angela Stickle brought up, so I'm not sure if she's still in the room, but happy to have her speak if I misrepresent what she said. But difference between automation, autonomous systems, and AI. Mainly leading into automation as the tool for repetitive tasks, autonomy good for dull, dangerous, dirty tasks, and AI as the tool that can be used to develop and run autonomous systems. So of course, all of those are going to be key, but full autonomy is a long way out, but that doesn't mean that there's a lot to do sort of in the meantime. But that getting there will require some key technologies that would accelerate autonomy in space and on the moon. Again, this is an area where definitely feel free to pipe up if you think I'm saying something that's not quite, or if I've incomplete. So one is computer vision algorithms that work on small data, and generally things that can work on smaller data. A lot of discussion of compute and power limited implications on autonomous systems. Systems that can detect things that have not yet been modeled before. So that's a big one. And then comms is limiting, bandwidth constraints, and prior planning for prioritization. And one that I just put into a bucket of ConOps and architectural elements. So there are things that we can do to get out the roads, the mapping, and the landmarks that will be essential to navigation safety. But there's also a big call for specific missions to design to, and how that can actually enable you to be actually make more tangible progress. Of course, there's no sort of workshop without a plethora of concerns. So those are all well noted, and those are the things that we gotta work on and really focus in on. A lot of that is also associated with those sort of complementary to the key tech that would enable this stuff. So a lot of the deep learning, which requires data and really high quality data, and a lot of it with proper annotation. And so we need a keen eye on research and development that'll allow us to do more with less. Lots of questions on trust, proving autonomy was quite interesting. Testing and observed performance, how much testing is needed. In my mind, this was quite interesting because we don't typically fly unless we have absolute certainty that things will work. And so how do we learn the rough and ragged edges? Which I think is an interesting question, especially for Space Technology Mission Directorate, which is our sponsor of LSIC. So they are all about technology development and learning those things, whereas certainly we wouldn't want those things to be learned by those who are more deeply involved with humans, at least when they're out there on the moon. And so the overestimation of autonomous systems is a concern as well. There's a lot of humans that are still involved, and especially sort of at the furthest edge is what is human intent and how can we replicate that, especially because it's so computationally limited. So that's my set of concerns, my sets of technologies, and some definitions. So I would open that to any of the rest of the folks here who are participating. What do you think? Danielle, did you have anything to add? I'm sure you must have something that you were like, Wes, you forgot to say.
No, I really enjoyed all the ideas. I thought it was a good flow, but I'm fascinated by how the entire conversation, focused around challenges in autonomy and solutions to these challenges. And I almost wish, if I had to go back and rewrite the script of the workshop, I could split it between those two sections. But no, I think we covered such a range of topics, and there was so much good feedback on minute things that everyone here, in industry, government, academia is working on that maybe doesn't, hit the light of day all that much. So I didn't have any very specific additions to your wonderful summary of the day, but I think we did a great job of bringing everyone together.
And I just stole the screen share to give some hot off the presses results from the polling that we took on. So Actually, I wanted to start not with the technology development challenges first. Actually, I'm sorry, I went to the wrong one. But integration with other systems was key. And when I look to the future, what we need to do is basically address these challenges. So I look forward to more opportunities where autonomy can be integrated into all the other things that we're doing within LSII and LSIC. That's a huge set of activities. And then all of these other aspects as well. So I think another theme that I really picked out was the need to share data so that we can learn together, and that's I think also in line with what we need to accomplish. So the programmatic challenge is of course funding, but interestingly, the workforce is at the bottom. So if we give people the right amount of money, then we'll be able to get it done. That's what I see when I read these programmatic challenges. The lack of specific mission, I already covered that as well. And then for fun, if you were the only human living on the moon, which pop culture autonomous systems would you prefer to assist you? As Sean pointed out, it was curious that more people voted for HAL, the eventually malicious, I guess, or maybe not intentionally malicious, but certainly more people wanted HAL than to be alone.
In 2010, it was
Yeah.
not a bad, HAL was more a victim of bad programming.
Oh, all those things that can get you in the end if you're not careful, right? So to finish off, yeah, as I said, autonomy is such a core technology that cuts across areas that I think it'll be really interesting to see how we can make sure that we continue to integrate into all the other LSIC focus groups. There'll be, autonomy will be infused in a bunch of the things that we're doing. We've got a fall meeting coming up, which is in Pittsburgh, where we'll be at, hey, there you go, Community College of Allegheny County and online. And also, that's right next door to Carnegie Mellon. So there'll be some amount of autonomy infused into that, as it always is or always should be. Thonu also presented yesterday the Living Off the Land session, which is going to be at Ascend. So that's another area where we'll have some presence on that. And I think very more broadly speaking, the stakeholders are working together a lot more. We had our whole of government approach at the LSIC spring meeting. We'll be hearing more along how everybody can coordinate together to get at this thing that we all want to do. And I think that also aligns with that idea of learning together, emphasis on teaming and transparency, integration, interoperability, all of that happy buzzwords. Ultimately, we need to have those buzzwords because that's what we need to do to get at a future where autonomous agents can work together alongside other elements where humans are around and safely as well. So we definitely have our work cut out for ourselves, but coming together as a community puts down those stepping stones that'll get us there. And if you aren't aware, I don't know if you have the slide for the transition to commercial workshop that happens the day after the fall meeting. It's going to be.
Sorry.
That's okay. That's okay. I will just talk about it, emphasize it now. It's the same registration portal, so no matter what, you will see it if you register for our fall meeting as well. But that's intended to be an additional day of working, trying to understand what NASA needs to provide to commercial to get them off and running, yeah, looking forward to that, planning it in partnership with Clive Neal. And it's especially interesting because of in light of the recent DARPA solicitation that came out for lunar to encourage commercial to develop lunar architecture. So they'll be present and announcing stuff at the winners of the solicitation on October 10th. And then on the 12th, they'll be participating in that transition to commercial lunar services workshop as well. So hope to see all of you there again, and many other venues. And I should definitely pass it back to Danielle and Stacy and all of those who actually did the work and put this together. It was a really fantastic event, and appreciate all of their effort.
Thank you so much, Wes. I appreciate you hopping on and taking the brunt of that summary work. That's difficult considering we've covered the entire topic of autonomy. So I guess I just want to leave you all with a little bit of attendee feedback. This is the same Slido link that you've seen throughout the past, 60 slides. So if you want to scan that and give us some last minute feedback, there are just a couple questions. There's a quick ranking about what you thought of the workshop. There's a question on what you wish we had covered in the workshop, but we didn't. I would love to hear some candid feedback on that. Autonomy is such a broad topic to cover, and so we did the best we could cramming it all into 2 days. But if there's something you really want to hear, then maybe another autonomy workshop is in our future. So we would love to hear your thoughts on that. And then the last one is just any other final comments or suggestions you have on future LSIC events. So we're always working to be better and to accommodate the needs of the community. So whatever you need us to do, we're happy to take that feedback. With that, I guess if just kind of open mic style, does anyone have any last comments they want to make? I made the joke you really hated my astronaut graphics during all the breaks, or you're really interested and looking forward to one specific event in LSIC.
I guess from my perspective, we have a real opportunity here to actually, in a sense, be the conscience for NASA with respect to sticking with, the real mission requirements. There's always a tendency, as deadlines become near to, restrict your activities in scope, trying to live within what you think you can deal with, when the reality of the situation is that we're actually trying to solve the problem of making the infrastructure work, and that's not something you back off from. And it's kind of like being a little bit pregnant. You either work the real problems or you're not doing what you signed up to do.
Yeah, thank you, Gary. Appreciate that.
I think the point of not backing off is a good one, right? We have done a lot to build momentum within the community, and I want to thank the whole community who's here and participated. That's how it happens.
I was guilty of putting a little bit of a advertisement in that there's a connection between actually an initiative the Space Force is doing that is looking at a modular simulation capability, starting off supporting conceptual engineering of power and ancillary services beaming, up through how it evolves into control system implementations for fieldable systems, which I think it would be great to have LSIC involved with.
Yeah, I think that there's a lot of opportunities for other areas to be working and coming in. NASA is definitely going to own, quote unquote, own the moon, but there's a broader cislunar ecosystem which is developing it. And I think that we've talked a lot about translational technologies, of which autonomy is certainly one of them, from terrestrial markets, from all markets, into what we would like to accomplish.
Oh. Any other final thoughts before we close out? I know I'm keeping you all from your 5 o'clock work deadline. Wonderful. I guess just in closing, I want to mention that there are a bunch of other LSIC workshops in the works. Thank you, Stacy, for reminding me. There's the dust mitigation and extreme environments workshop happening sometime. I unfortunately am not up to date with any of these.
November 7th.
November 7th. Okay, great. And then I feel like I'm missing one or two. Does anyone know, Wes?
You can always check our website, lsic.jhupl.edu, for updated calendar of events that are coming. Biggest ones that always come up in my mind are the fall meeting and the dust one. Those are the biggest ones I think in my mind that are coming up.
Wonderful. And thank you,
Lindsay.
Lindsay. Awesome. Well, with that, thank you so much for participating and sticking around until the end. I really appreciate all of your thoughts and contributions to the workshop. Huge thank you to our planning committee, our presenters, panelists, subject matter experts, and APL LSIC facilitators. You all made this happen, and I really appreciate that. And with that, we'll conclude things. We'll get the recording out. We'll get presentations out, and everyone, I hope you have a great rest of the week, and we'll see you at our next events. Thanks.
Thank you for your efforts all.
Thank you, everyone.